Well, let us now look at another application example for the shear force diagram and the bending moment diagram, where you have a part triangular load. So you have a cantilever beam which is clamped at this support C. You have a triangular load which goes from W0 to here, and at certain distance A it drops down to 0, but it's a linear variation, and the total length of the beam is L. So how do we go about solving this? So see here, this is a problem where method of sections can be quite nightmarish, because suppose if you take a a section somewhere here, or a section somewhere here, right? Suppose if you're going from left to right, then you have to, if you're taking a section here, you have to deal with a trapezoidal kind of a loading if you want to avoid having many loads such as the reactions and so on. Or say if you're starting from here, then you have to compute the reactions, the vertical reaction and the moment, and then go from here to here, take one section and then take another section here. So you will see in this is one example where you truly start to see the merit of using the relationships to draw the bending moment diagram and the shear force diagram. So let's go ahead and try to do this problem. So I have drawn two beams below here. One is for the shear force diagram, one is for the bending moment diagram over here. So let's first start with the shear force diagram. So here, see, just by looking at the problem, you see at the very end over here there is no concentrated load, so your shear force at that particular point is going to be 0. So this is my SFD, and just for convenience of drawing, let me draw the lines that we have, right? The guidelines. So of course this is my point A. Intermediate, I have where the triangular load ends, I have the point B, because those are the places, the reason for drawing the guidelines is that those are the places we expect transitions to happen. So just for a neater diagram, it is often convenient to draw this guideline. All right, so now that we have the guidelines, let's for the first beam, let's mark the points as well. So this is my A, here is my B, and here is my C. Now, as we hypothesized, at this particular point, my shear force will be 0. So at this particular point, I will have no shear. Right? Now, let's see how the shear force diagram varies. So let's write down our expression again. So we have our dV in dx is minus of w, which is a function of x that we have over here. This is the general form of the equation. And so that kind of tells you that here our w is in this particular problem, this w is a degree 1, because it's a linearly decreasing load. So that again tells you that your v must be second degree, that is, it must be quadratic. So you will have, as long as the load is present, where the load is present from A to B, you will have a quadratic variation of the shear force diagram. Now, how is the quadratic variation going to happen? We know that it is 0 over here, and what is going to be the value of the shear at this point B? We can find that out as well. So we have VB minus VA will be negative of the area of, this is again the relationships which we had looked at, loading diagram, which is in this case nothing but, what is the area of the loading diagram? It is half times A times W0 over here, half times base times altitude. So minus W0 A divided by 2. So I know that here the shear force is 0, and at this particular point, somewhere at the point B, I have the value over here is W0 A divided by 2. And at that particular point, I have not put the negative sign because I'm drawing in the lower half plane. And also, so from A to B, that is from the shear force of 0 over here to a negative W0 A over 2, I'm going to have a quadratic variation. Now again, we are back to the same question, that how will the quadratic variation be? Will the quadratic variation be something like this, or will it going to be something like this over here? So whether it is going to be concave up or concave down. An easy way to find that out, because here what is going to be the slope at this particular point? The slope at this particular, remember the dv dx is negative, the slope is negative of the of the load at that particular point, negative of the distributed load at that particular point. So here I am going to have a slope of minus W naught. So here my slope will be minus W naught. So let's just maybe the slope kind of mark it over here. So here I will have a slope of minus W naught, and at this particular point you see what is going to be the slope, the dv dx at B over here. It will be the value of the distributed load at B, and the value of the distributed load at B is equals to 0 over here. So here the slope is going to be 0. So here you will have a kind of a flat slope. So what kind of a curve in which you start with a negative slope and slopes increases and becomes 0, because you are going from negative slope to a 0 slope, which is something like this over here. Because here you see in this particular diagram, so I am having a negative slope over here and I'm going to the regions of 0 slope. So I am going to have a curve which is going to be concave down. So let's just go ahead and draw that. So the shear force diagram variation is going to be like this over here. So let's just mark those. So here you have a slope which is equals to minus W, and here at this particular point my slope equals to 0, right? So I have drawn, and this variation, that which I just drew, this is quadratic. So I have found it from A to B. Now what happens after B? After B, you see there is no load over here. So what does a no load mean? If this is 0, right, that means your V must be a constant. So from here all the way up to here, you're going to have a constant line with this particular value of W naught A over 2. So let's just go ahead and draw that one as well. So here I'm going to have a constant line. Okay. So this constant line here also, it is W naught A over 2, negative. So the whole shear force diagram is a negative. So you see how easy it was using the relationships to draw your this shear force diagram that you have over here. Now we are going to go ahead from the shear force diagram over to the bending moment diagram, which is the bottom beam. So here I'm going to draw my BMD. Now again, focus on how the bending moment is going to vary. Let's just write our fundamental relationship. We have dm dx equals to V, right? And also we have the other relation. The difference is the area of the shear force diagram. So let's see that how this is going to vary. So now my V, I know, is going to be quadratic. So since V is quadratic, so V is quadratic, so that tells me that my M will be cubic. Again, same relationship. Will it be a concave up or a concave down curve? Let's try to find out. Again, your answer to that will always be with the slope, right? So the slope here, dm dx equals to V at this particular point A. My value of the shear force, right? The value of the shear, because remember this slope is equal to the value of the shear force at that point. So at this particular point, my slope is 0. So here I have a 0 slope. And at this particular point B, again dm dx at B over here will be the value of the V at B. So the value of the V at B is negative W naught A over 2. So here you have a negative slope. So what kind of a, whether it is a this kind of a shape or this kind, it is going to be a concave up, because for a concave up place you see that you go from a 0 slope to a negative slope over here. So I'm going to go, so my curve is going to be, bending moment diagram curve from A to B is going to follow a pattern like this over here. So let's just go ahead and mark that. So from A to B, I'm going to have a cubic curve, something like this, where my slope here is equals to minus W naught A over 2, right? Because this is the value of the shear force at this particular point over here. So this is what I found the slope to be, right? Now from here to here, or how do I find this particular value over here? You can simply find by integrating this one, or if you just want to use the the rule for the area of the parabola, because here you have from this one you are going to a zero slope. So if you take the area, the area of this one will be the area of the inscribing rectangle. So remember the how do we find the moment? The moment, say mb minus ma will be the area of the SFT from A to B. So I can simply approximate that as 2/3 of whatever rectangle this inscribes. So that is going to be W naught A over 2. So that is will be minus, since this is a negative one over here. So 2/3 of minus W naught A over 2 times this distance. This distance is A over here times A. Okay. So it will be minus W naught A square by 3. So here the value of my bending moment at this particular point is nothing which I just calculated here. So that is going to be minus W naught A square by 3. Now what is remaining is this portion from B to C. Now you take a look from B to C. Here the shear force is a degree 0. So let's just write that down. So from B to C, right? From B to C, my V is a degree 0. So that kind of tells you that your moment will be a degree 1. So it will be a linear line, right? It will start from here. It will have the same slope though. Why? Because the slope depends upon the V. So the slope or the value of the V here is W naught A over 2, and all along is W naught A over 2. So it will have the same slope of minus W naught A over 2. Just it will start from here and will continue as a straight line. And what is also the value of this moment at this particular point C? That also you can find out easily, that your MC minus MB is going to be area of the shear force diagram between these 2 points over here. So that is going to be minus of minus, because your shear is a negative over here, minus W naught A over 2 times L minus A, because this is the remaining distance. So I'm trying to find this area between this circumscribed rectangle over here. So this is the ordinate, and this total distance is L, this is A. So this distance from B to C is L minus A, which I wrote over here. Right? Now if you substitute the value of MC, so remember the value of MC, or sorry, the value of MB, which we already calculated from here, is minus W naught A square is minus W naught A square by 3. So if you put that over here, what you will eventually get that, and I have it worked out here, so I'm just going to write the final expression. So we will get the value of MC, that is the that is the moment at this particular support, that comes out as minus 1/6 W naught A TL minus A. So this is the value, and as we just discussed, that this is going to have a linear variation. So it is going to sort of go quite a bit down from here. So let's just quickly mark that it is going to go something like this over here, right? And then of course this line has to close somewhere over here. So here at this particular point, what you have, that it's equals to minus 1 over, sorry, I should not have written the negative sign here also, because I'm marking in the bottom half plane. So here the value will be, if you write the negative sign, that's also okay, as long as you are clear with it why you're writing it. Minus W naught A by 6 3L minus A. So, and this whole bending moment diagram is also negative. So try this problem out on your own and try to match the answer and see if you get what you have over here.